For years, astronomers and dreamers alike have stared at Uranus through every telescope we could build, seeing nothing but a faint, hazy blue smudge drifting at the solar system's frozen edge. A world that seemed to offer no drama, no storms, no secrets worth chasing. But that silence just ended in the most explosive way imaginable. The James Webb Space Telescope has finally released the image we've all been waiting for. And what it reveals isn't the quiet blue ball we expected. It's a living, breathing planet wrapped in a rosy infrared glow, where colossal auroras surge and roll like cosmic wildfires, reshaping everything we thought we knew about how distant worlds work. Imagine opening your feed and there it is. Uranus no longer a flat, featureless disk, but a three-dimensional storm of light captured in breathtaking detail. The planet's delicate ring system glimmers like scattered diamonds. Bright polar clouds swirl near the cap. And above it all, vivid rosy patches of auroral energy pulse and spread, climbing thousands of kilometers into space. This isn't just another photograph. This is the first time we've ever seen the upper atmosphere of an ice giant in full vertical glory. Layer after layer peeled back, energy flowing upward in patterns no model predicted. One glance and you feel it. The universe just handed us a key to mysteries that have haunted science for decades. To understand why this single release hits so hard, rewind to 1986. Voyager 2 gave us our only close-up, a single fleeting pass that painted Uranus as bone-chillingly cold, temperatures plunging to minus 224 degrees Celsius at the cloud tops. The planet looked utterly inert, a generic blue-green sphere with no obvious weather, no bands, no spots. From Earth, even the best ground telescopes could only catch blurry hints of something stirring far above those clouds. Starting in the early 1990s, those hints turned into a full-blown puzzle. Year after year, the upper atmosphere kept getting colder, bleeding heat into space faster than any simple explanation allowed. A planet this far from the sun shouldn't be dynamically cooling like that. Yet it was. And for 30 long years, we had no way to see why. We waited because Uranus refused to cooperate. Too distant for sharp detail. Its atmospheric glow too faint for anything but the most powerful instruments. Every previous attempt left us with snapshots. One from Voyager, a handful from Earth. Never enough to connect the dots. The planet rolls on its side at nearly 98 degrees. Its magnetic field tilted another 60 degrees off that crazy axis and shoved off center like a drunk compass. Models suggested chaos, but we couldn't watch it happen. We needed something revolutionary. Something that could stare for hours, slice through infrared wavelengths, and map energy in 3 dimensions. And now, after all that waiting, James Webb has delivered exactly that. The telescope locked onto Uranus for nearly a full planetary rotation, 15 unbroken hours, using its ultra-sensitive near-infrared spectrograph. It didn't just snap a picture. It dissected the faint glow of specific molecules high above the clouds, turning emissions into precise fingerprints of temperature, density, and motion. What emerged is the first ever vertical map of the ionosphere, stretching up to 5,000 kilometers above the visible atmosphere. This charged layer, where solar wind meets magnetic forces, suddenly stands revealed in stunning depth. The image doesn't just show the surface. It shows the hidden machinery driving the entire upper realm, and what that machinery reveals is jaw-dropping. The upper atmosphere isn't the uniform deep freeze we assumed. Temperatures climb dramatically with altitude, peaking at around 150 degrees Celsius between 3,000 and 4,000 kilometers up. Warmer than expected, yet still cooler than older, cruder measurements had claimed. Even more striking, the long-rumored cooling trend is no longer a guess. Webb's data lock it in as fact, Uranus is still losing heat from these heights, decade after decade, in defiance of every straightforward energy budget we built for ice giants. But here's where the story turns truly bizarre. The density of charged particles, those ions that light up auroras, is far weaker than any model predicted, and their peak concentration sits much lower, around 1,000 kilometers up, while the temperature maximum towers thousands of kilometers higher. Two different peaks, two different stories unfolding in the same sky. Something is pumping energy upward in one place, while charged particles behave differently in another. The image doesn't just hint at this mismatch, it paints it in three dimensions, forcing scientists to confront a truth we never saw coming. To grasp the scale of this revelation, you have to confront just how alien Uranus truly is. Its rotation axis points almost sideways, so one pole faces the sun for decades, while the other freezes in endless night. But the magnetic field doesn't follow the spin. It's offset and tilted wildly, tumbling and wobbling like a broken top as the planet turns. On Earth, our magnetic shield is neat and stable, channeling auroras into clean polar rings. Uranus throws that rulebook away. Its field lines twist and tangle chaotically, funneling solar particles in unpredictable surges that sweep across the entire planet instead of staying politely at the poles. The released image captures exactly that chaos in action. Two bright auroral bands glow rosy, where the strongest magnetic connections should hit. Yet between them sprawls a striking depleted zone. A dark gap where both the infrared glow and ion density drop sharply. This isn't random. It's the direct fingerprint of those lopsided field lines acting like a selective gate, sometimes channeling energy deep into the atmosphere, sometimes blocking it entirely. Similar gaps appear on Jupiter, but Uranus's tumbling geometry makes the effect far more dramatic and far-reaching. The auroras don't stay neat. They roll and surge like living rivers of light, driven by a magnetic engine that's fundamentally off-kilter. For the first time, we watch that engine at work across thousands of kilometers of altitude. The image shows energy cascading upward, heating layers at different heights, while the magnetic field sculpts the ion density like an invisible hand. What once lived only in computer simulations now stands revealed in vivid rosy detail. The mismatched temperature and ion peaks suddenly make sense. The chaotic magnetic field is the hidden driver, pumping and shaping the atmosphere in ways our old models never captured. A single release has turned theory into visible fact. This changes everything about how we understand giant planets. Our textbooks assumed ice giants like Uranus ran on simple rules: distant, cold, stable. But the data prove the energy budget is far more complex, far more dynamic. Heat flows, particles shift, magnetic forces reach deeper than anyone calculated. Uranus isn't a quiet relic. It's a natural laboratory for physics we barely understood until now. Every assumption about how these worlds retain or lose internal heat gets rewritten in light of this one image. And the stakes go far beyond our solar system. Ice giants are turning out to be the most common type of planet across the Milky Way. For every hot Jupiter or rocky super-Earth we spot, dozens of Uranus-like worlds drift in the data. Until now, we guessed at their atmospheres. We modeled them with incomplete tools. This image hands us a real benchmark, a detailed three-dimensional blueprint of vertical structure, auroral behavior, and magnetic interplay. Exoplanet scientists can finally calibrate their instruments against a true example instead of blurry approximations. The energy balance we see here becomes the template for interpreting distant worlds we may never visit directly. Look again at that rosy glow spreading across the frame. Those auroral splotches aren't just pretty. They're proof that even the coldest, most sideways planet in our neighborhood runs on hidden engines of astonishing power. The rings catch the light like fragile jewelry. The polar clouds hint at weather systems we still can't fully explain. And above it all, the ionosphere pulses with the influence of a magnetic field that's been tumbling for billions of years. One image has transformed a world we dismissed as boring into one of the most dynamic laboratories in the solar system. Yet the real power of this release isn't just what it shows today. It's what it demands next. The map is drawn. The questions are sharper than ever. Why does the cooling continue? How deep does the magnetic chaos reach into the interior? What strange internal heat source keeps an ice giant active after all this time? The image points the way, but it can't sample the atmosphere directly or probe the core. Only a dedicated mission, orbiters, atmospheric probes, perhaps even landers on its moons, can finish the story. This is the moment the journey to Uranus truly begins. For decades we waited for a single clear view. Now that view is here, glowing rosy and alive with surprises. It reminds us that even the most overlooked worlds hold secrets capable of upending our understanding of the cosmos. What other ice giants are out there, rolling sideways through their own strange auroral storms? How many exoplanets are quietly rewriting the rules of planetary physics right now? The James Webb Space Telescope has given us the image we dreamed of. It has lit the path. The only question left is how soon we will follow. The universe just opened a window on a world we thought we knew. And behind that window lies a reality far wilder, far more beautiful, and far more mysterious than anyone predicted. This single release doesn't close the book on Uranus. It tears the old pages out and demands we write an entirely new chapter. So hit subscribe right now so you never miss the next breakthrough that flips our cosmic perspective upside down. Drop a comment below, telling us which part of this image blew your mind the most. The rosy auroras, the magnetic chaos, or the promise of worlds beyond. Share this with every space lover you know, because moments like this remind us why we look up. And keep asking the big questions. Because if one sideways planet can hide this much wonder, imagine what else is still waiting for us to finally see.